Day 8, I'm going to go through the PowerPoint for low pass and high pass filters using RC circuits and RL circuits. So let's get started with the PowerPoint presentation. And as I said, we're going to go through RC and RL filtering circuits, and based on chapter 26, sections 6 through 8. First, let's put this on slideshow. Okay. So we'll look at, again, the filtering considerations. And we're going to take a look first. Filtering is done through voltage division, okay? We have a circuit, basically a series circuit. We're doing voltage division to get a voltage output, and that output will be filtered. It'll be just the stuff that we really want, whether it be low frequency stuff or high frequency stuff, or possibly a particular frequency, just a very small frequency range. So in order to do this, okay, with the output then is, if the output is across a particular component, and basically we're talking about the voltage output. But what we're really interested in is what the power is, okay? Because if it's high powered that's being output, okay, that's what stays. That's what gets used up. If it's low power, it's just low power, and it's not seen, it's not heard, okay? So we want to pass high-powered stuff. So in order to do that, we need to consider, if we have a series circuit, we have voltage division, we need to consider power. And the results that we get when we start doing this are what we call Bode plots, B-O-D-E plots. And basically they plot filtering for RC filtering circuits and for RL filtering circuits. And finally, we'll go to a very quick filtering review of what we've learned just today. So, okay, we bring up the fact that when we pick up a signal, it's got a lot of noise in it. It's got a lot of extra stuff that we don't want, probably. But we're interested into just one signal out of that. So we have to filter the stuff that we don't want and just keep the stuff that we really do want. And to do that, we use combinations of low pass, high pass, and band pass filtering. Okay, where the low pass means that we pass along those frequencies that are low. In other words, the signals that have low frequencies, we pass just those, and we discard the higher frequencies. And the ones that we pass are usually either from 0 hertz up to a certain frequency, which we call the cutoff frequency, FC, okay? And if above the FC for a low-pass filter, that doesn't pass along because the power just isn't there, okay? For a high-pass filter, we do the opposite. We actually pass anything that's above that higher frequency, that cutoff frequency, FC, and higher. Okay, and the stuff that's at lower frequencies, well, its power is so low that we can't pass it along. There's nothing we can do with it. And then finally, if we're interested on just a specific set of frequencies, a range of frequency, then we use a bandpass filter. And normally a bandpass filter is used to tune in a specific frequency. Okay, let's recall again our sinusoidal signals. Most of our signals any radiation that we have has basically is sinusoidal in nature, okay? And this is a typical 60 hertz signal that's got a 10 volt peak, okay? But if we take that 60 hertz signal and add a lower frequency to it, and you can see there's two different style of peaks here. And those two tells you that there are two frequencies operating, okay? And one of them is low and the other one is higher frequency. So the 60 cycle is higher and the other cycle is got lower frequencies. All right, see, and we can also do the opposite. We can have our 60 cycle with a higher frequency signal into it, okay? So filtering is done by separating the lower amplitude signals from the higher amplitude signals. In other words, just like I said, if we have a high amplitude, then basically we've got power there. So they pass along. And lower power really gets rejected when it's not good enough to do anything. It's just not enough energy there. So we use AC filter is accomplished by the frequency by using RC or RL circuitry, and because we use the reactance factor, XC or XL, so each of them is proportional to frequency, which as you can see, in the case of a capacitor, the frequency is the reactance is inversely proportional to frequency. In other words, as the frequency goes up, the reactance goes down. The opposite is true for an inductor. As the frequency goes up, so does the reactance. All right, so let's again explore what we mean by voltage divider, voltage division. In this case, what we have is an example of a resistor, fixed resistor in series with a variable resistor. And we're going to change that variable resistor can change from 10 ohms up to 2000 ohms. And as we change the resistance, of course, the voltage increases. So as the resistance increases, okay, as our resistance increase, our voltage will increase because our resistance has increased, and so forth. I times R is voltage. So V out, as R increases, IR increases to a level. And what we're interested in is that anything above the 70% of the maximum is going to be active stuff, stuff that we can hear, and stuff that we can use. Anything below 70% is stuff that gets rejected. If, on the other hand, we look at, So again, we do this again. Output voltage is in phase with the single voltage of Rx. Rx is not reactive, okay? So this is in phase. But we know if we change to a capacitor or an inductor, it won't be in phase. So let's consider that. Okay, here's a case now. We're not changing the capacitance. We don't have a variable capacitor here, but we do have a variable frequency to simulate that you have a frequency range. In this case, we can have a 10-volt frequency range from 100 to 10,000 hertz, 10 kilohertz. Okay, and we pass that through our series RC circuit, and we're going to output. We can output from the capacitor. We can also output from the resistor, which is not shown here. If we output across the capacitor, well, what happens? Okay, as the frequency increases, that capacitance decreases. All right, the reactance decreases, rather. The capacitive reactance decreases. So the output then decreases because you have the output is going to be a voltage which is equal to the current times the capacitive reactance. And as the capacitive reactance decreases at higher frequencies, okay, we get a lower output. So we're going to simulate that, but before we do that, like I said, we're interested in high power versus low power. Low power gets rejected, high power gets passed on. So we want to find out what is a threshold voltage. At what voltage does all of a sudden does it pass from high power to low power? So power we know is proportional to V squared because power is V squared over R, okay? And we want to find that point at which the output power is half the input power. So half of Pin has to be smaller than P out, okay? Or P out needs to be greater than half of the input power. So the ratio of P out to P in is a half. So we can say that the output voltage squared divided by the input voltage squared has to be equal to 1/2. Or when you take this, then V out over V in, then it becomes just take the square root of that. 1 over 1, the square root of 1/2 is 0.707, which we can say then that V out then is, we multiply both sides by V in. V out has got to be 70.7% of V in. That's what we're looking for a threshold voltage. So here is a Bode plot. It's a typical Bode plot. And the Bode plot shows two things, okay? Basically, it shows what the output is at a different frequency range, okay? So it goes, in this case, high output to a low output, okay? And it also looks at the phase. That's the magnitude, and that's how the phase. And normally at the 45-degree angle is when it crosses over between high power to low power, okay, or vice versa. So we can simulate this. We can create a Bode plot from an Excel spreadsheet by using an RC filter. Okay, we're going to use a series RC circuit. We're going to specify a resistor and a capacitor, and we're going to look at a frequency range from a low, say 0 or 100, up to a high, say 10,000 hertz. And we're going to use a suitable input voltage, okay? 10 volts is sufficient for now. And we know that the cap reactance is going to be equal to 1 over 2 pi FC. And we know that the impedance is going to be the square root of R squared plus the capacitive reactance squared to give us an impedance. Once we find the impedance, we can get what the current is running through the circuit, which is the input voltage divided by the impedance. And so the voltage output across the capacitor is just going to be that current times the capacitive reactance. And if we want an output across the resistor, then it's just simply the current times the resistor. Okay, and our critical, our crossover frequency is at 1 over 2 pi times RC. Okay, so here we're going to be using RC circuit with a resistance of 10 k ohms and a capacitance of 0.01 microfarad. So here in our spreadsheet, what we do is we put a series. This only goes from 100 to 1,000, but we really want to go up to about 10,000. Okay, I didn't show the rest of the spreadsheet. But from this frequency, we first calculate what our capacitive reactance is, which is proportional to frequency, and we get a list of values. From XC and from R, we can get a zener, or we can get an impedance Z out of that. Okay, there's our resistance. And we know our impedance. We know our voltage. So, whoops. We know our voltage, the input, so we can get our current. Okay, so we get current. From the current then, and from XC, we can get the voltage across the capacitor, and we can also, the current times the resistance gives us a voltage across the resistor. So we plot first the output from the capacitor, and we notice that we get high voltages below the frequency FC signal, which is around 1600 or 2500, 2600. Okay. At below 2600, the power is greater than it is above the 2600. So anything with higher power gets passed on. Anything with lower power gets filtered out. Okay, it's just not strong enough. If we go across the resistor, the opposite is true. Okay, across the resistor, as we go higher frequency, okay, we're going to get a higher power across the resistor. At lower frequencies, we're going to get very low power because the current is very low. Okay, so this across the resistor, then we get high pass frequencies, and low frequencies are not passed; they're blocked, they're filtered out. And if we look at the phase angle will change in degrees, and normally everything changes at the FC value occurs right at around the 45-degree phase angle change. Okay, so finally, we're going to look at the RL filter. So this, again, the same type of circuit, only instead of a capacitor, we're going to use an inductor. And so we're going to have a resistance in ohms and an inductor in henries. We're still going to use the 100 to 10,000 hertz frequency range. We'll use the same type of voltage input, but now our XL is directly proportional to the frequency times the inductance. The impedance then is still the square root of R squared plus the reactance squared. And the current then becomes the ratio of the voltage input divided by the impedance. And then we can calculate the voltage output across the inductor and across the resistor. And our cutoff frequency is going to be 2 pi times L, R divided 2 pi times L. So here we're going to use a 1K resistor, and we'll use a 50 millihenry inductor. Okay, our FC range is around 3180 hertz. Once you put into this equation there, R over 6.28 L, we get 3180 hertz. That's our cutoff frequency. Not shown in here, our frequency actually goes up to 10,000, okay? But we're interested in frequencies between 3,100 and 3,200, okay? So we're plotting XL, we're plotting, again, the impedance, we're plotting the current, and then we evaluate the voltage across the inductor and the voltage across the resistor, okay? And we get then across the inductor, and we get something totally opposite what we got for the case of the capacitor. Okay, we're going to pass stuff that's higher frequency and filter the stuff that's lower frequency. So this is a high pass filter. Call that a high pass filter because we're passing frequencies that are above 3,200, let's say. Okay, and we filter out anything below 3,200. And vice versa, if we look at the resistor, then we're actually going to pass a lower frequency across the resistor, but filter out the higher frequency. Okay. And again, everything happens right at that 45-degree phase angle change. So the cutoff frequencies then they occur when, in the case of an RC filter, when the resistance equals the capacitive reactance, so that FC is equal 1 over 2 pi RC, and it occurs at minus 45 degrees phase shift. And the R is the opposite. R is when R is equal to the inductive reactance, so giving us a cutoff frequency at R divided by 2 pi L, which occurs at the plus 45-degree phase. So what we have then, we have responses. What we can see, we have low pass. For a low pass filter, we pass low frequencies, but stop higher frequencies. High pass filters, we stop low pass frequencies, but pass high frequencies. And but that all depends. Now, in the case here for low pass filter, well, the pass here can be if this case, we can have a low-pass filter if we output from the resistor of an RL circuit, okay? Or we can have a low-pass filter if we output from a capacitor of an RC circuit, and vice versa here for our high pass. Band pass, we'll discuss that next week or tomorrow, I guess. And basically, we're just going to pass a certain frequency range, small frequency range, and stop low frequencies and high frequencies. Or we can do a band stop where we're just going to pass low and pass high, but stop intermediate frequencies. So that's it. Let's get back to, now you can go and take a more careful look at this as a PowerPoint presentation and do it and take notes and read carefully, okay? If I miss something, if you don't understand something, just give me a call. I'll answer it. But for now, let's get going on the rest of the assignments.